Hi. My name is Ken Mimasu. I'm also a lecturer in the high energy physics group in Southampton. And like Nick, I'm interested in understanding physics beyond this so-called standard model of particle physics that was just described to you by Nick. And I do a lot of looking at LHC data and trying to understand what kind of conclusions we can draw from that. And today, my task is to count quarks with you. Essentially, we're going to try and turn into particle physicists for 40 minutes or so. So we've just heard a nice talk from Nick describing this world of particles and how it all comes about. And our goal today is to actually look at some data. So we're going to try and learn something about the properties of the particles that we see in nature using real data from accelerators. So since you've already had quite a bit of theory from Nick, we won't delve too deeply into that and just think a little bit more about what you see and what we can draw from that. And so as you did hear from Nick, quarks are what make up this nuclear matter. So all the nuclei of atoms, in particular the up and down quarks, make up those atoms, but there are also other copies of those that Nick also described. And so the kinds of particles that are made up of quarks are called hadrons, and that's where the Large Hadron Collider name comes from, because protons are examples of hadrons that we collide together in this machine. So all of these guys are made up of quarks and antiquarks. And so what we're going to try and do with some data is to experimentally determine how many types of quarks there are. So in order to make this session interactive, we're going to be using this platform called Vivox. So later on, we'll get to look at some particle physics events, and we're all going to decide together what we think they are. So in the meantime, we can test out the platform. So you have this QR code here. So please go ahead and scan it with your phones, for example. If you want to use that, it'll work. Or you can also click this. Well, you can also access this link in the slide. I realized I planned to put it in the chat, so let me do that as well. Sorry for the infinite tunnel of images while I just copy the link to the Vivox app here in the chat. Here we go. Okay, so that link is now in the chat as well, in case you want to use your computer to respond to the polls. So phone or computer, either way. Hopefully, once you access this, you should see a welcome page that looks a little something like this. And then we'll, in a second, launch a test question for you guys to make sure that it's still working. So do let us know if you have any problems in the chat connecting to the system. And if you have connected to it, we can do a little test question while we wait, which is for you to tell us what you had with your breakfast this morning. So tea, coffee, fruit juice, water, nothing, or something else. So in order to do that, I have to open the poll. So let me do this. There you go. So somebody's already told us that they've had water. I can see that it's working, which is very nice. You can interactively see how many people are connected to it. There's 32 of you or so, and you're all telling us what you had for breakfast. So that's nice. Nice to see it all working. Okay, not many coffee drinkers. Surprising. So let's wait for all of those answers to come in, hopefully. In any case, it's good. So I think it's working. Of course, this is not a real physics question, so it doesn't matter too much if not everybody responds. So I think I'm happy that this system is working, and there's enough of you that are able to answer. So again, just mention in the chat if you have any problems, or perhaps try with either your phone or the link in the chat on your computers. Either way is fine. So I'm going to close this poll now and get back to some actual physics. All right. So in order to become particle physicists, we of course have to look at some particle physics events, such as the ones that Nick showed us earlier. What we're actually going to be looking at today are not events from the LHC, but actually events from another collider called the Large Electron Positron Collider, or LEP. Now, you might recognize this picture as the same picture that Nick showed earlier, and the reason for that is that LEP is actually the predecessor of the Large Hadron Collider. So it was a collider that was built in exactly the same tunnel as the LHC, and the only difference between those two colliders is that whilst the LHC collides protons, the Large Electron Positron Collider, as it says in the name, collides electrons and positrons together. So you can perhaps recognize this diagram over here from the one that was shown in Nick's slide. So you have time goes in this direction. You can imagine kind of space going kind of in the upwards direction. So you have an electron coming in, a positron coming in. They annihilate at some high energy, and they produce some intermediate particle, such as a photon. And then if you have enough enough energy, then you can convert that into mass energy of heavier and new particles. Right? So that's the principle behind the LEP experiment. Similarly to the two detectors that Nick showed earlier, or the one detector that he showed a picture of earlier, the detectors placed around the interaction points at the LEP experiment were very similar in structure. So this is an example of one such detector that was involved in the LEP experiment called Opal. And the main thing that we're going to need to understand for this activity is that these detectors are made up of different layers. And so we have different layers which have different roles in terms of how they interact with the particles that are produced at the interaction point, such that we can infer or try to identify the type of particle that actually passed through the detector in that place, depending on how it interacted with the detector. Okay. So in particular, you can see that there's layers kind of like an onion. And each layer, as I said, has a different role. And the key layers that we're going to be thinking about in our exercise are the following. So you firstly, of course, have the beam pipe, which is at the central point of this cylinder shape. And then the first layer is so-called tracking chamber. So what that does is that whenever you have charged particles passing through this volume, it actually records a set of hits and kind of tracks their position over time. So it really looks like a track of a path of the particle passing through that region of space in the detector. The second layer is called the electromagnetic calorimeter. So it's the first kind of stopping layer. It's a bunch of lead, more or less, that tries to stop certain classes of particles and records the energy that they deposit when they are stopped. And so it's able to stop very light particles, this first layer, such as electrons and photons, when they interact with charged particles inside this material. If a particle is heavier or has enough energy, then it can actually pass through this first layer of electromagnetic calorimetry and reach the second layer of calorimetry, which is called the hadron calorimeter. So this is a slightly thicker, denser layer, which has more stopping power, and therefore will stop particles that have managed to pass through the electromagnetic calorimeter because they're heavier or more energetic. Typically, that's different types of hadrons, such as a proton, for example. Again, it measures a certain amount of energy deposit in a particular region in space where that particle hit the layer. And then lastly, we have the outermost layer of the detector, which is the so-called muon detector or muon calorimeter. It turns out that muons, because they're so heavy, they actually manage to punch through all the layers and escape the detector entirely. So they leave a trace in all 4 layers of the detector and leave hits in this outermost layer. And that's the way in which we can actually identify that it was actually a muon that passed through the detector rather than anything else. So this diagram just summarizes the information that I just gave you here. So photons, they're neutral, so they don't make tracks, but then they get stopped in the electromagnetic calorimeter, or the ecal. Electrons are similar to photons. They get stopped at the same layer, but they make tracks because they're charged. Muons, they're charged, but they pass all the way through, so they give you hits everywhere. Hadrons tend to make it through the first layer of calorimetry and get stopped by the second one. And the same thing for neutral hadrons, such as the neutron, except that they don't make tracks and they don't interact with this electromagnetic calorimeter, which relies on electric charge to stop the particles. Okay, so that's the sort of broad way in which the detector works and how we can identify, for example, distinguish between an electron in the detector and a photon in the detector based on the fact that one of them left the track and the other one didn't, for example. Okay, so here's an example of some simple events. Again, you can think of this process, and this is the interaction point here. We're looking head on at the cylinder, and so you can see how the detector layers are placed. You have this beam line here, the tracking chamber in the central part, and then these first two layers of electromagnetic and hadron calorimetry. And then at the very end, you have these hits in the muon chamber, which are represented by the little crosses. Tracks, as you can see, are drawn with lines. And then the little hits, the energy deposits in the different layers, are represented by these little boxes of energy. So the bigger the box is, and also depending on the color of the box, so the energy goes from low energy to high energy, low energy in red, high energy in white, depicts how much energy was actually deposited by this particular particle passing through in this direction, in the opposite direction in this case. And so some events are very nice and clean, where you clearly see that there's just one particle coming in and interacting with the detector material. In other cases, it's a lot messier, and you have sprays of particles. Okay. So we'll get into that in a bit more detail in a second. So how do we identify particles? Well, the first type of particle that we might be after are electrons. So I already mentioned that they're light, they're charged, they can't decay, so they go all the way, they sort of don't decay at some point whilst they're traveling, and they're stopped by the first layer of the detector, so this electromagnetic calorimeter. So if you want to identify an electron, you want to identify a particle that has left the track because it's charged, and then it's deposited all of its energy in the first layer of the calorimeter. So these are very nice, clean particles, very easy to observe, just one big energetic deposit in the first layer, accompanied with a track that points to it. So this is an example of an event with a pair of electrons, or probably an electron-positron pair being produced at this left collider. Moving on to the muons. So as Nick mentioned, they're basically heavy copies of the electron. So they have all the same properties, but because they're 200 times heavier, they actually manage to punch all the way through to the edges of the detector. Once again, they don't decay, at least within the distance, so the time it takes for them to get from one end of the from the center of them to the edge of the detector. And so we tend to observe them as a charged particle passing all the way through. So it leaves again a track, as well as hits in all of the calorimeters, so the electromagnetic, the hadronic, and then the muon chamber. So you expect a single track plus hits all throughout the detector. Again, this is an example of a muon anti-muon event, or mu plus mu minus event at LEP. So as Nick mentioned, the strong nuclear force is a bit of a strange beast in that anything that interacts with this force, such as a quark, grows, so the force between those two objects grows with the distance. And so that means that as you have two, say, for example, a quark-antiquark pair separating in space, for example, if they were produced at a collision, they would be back to back, then the energy between them builds up such that at some point it becomes energetically favorable to actually produce a new pair, a new quark-antiquark pair from the vacuum, such that in the end your final products arrange themselves into things which are neutral under the strong force, so don't actually mutually interact with each other very much. And so from a quark-antiquark pair produced at, say, a collider like LEP, you will end up with a final state that involves hadrons, which are bound states of quarks. So in this particular case, I had a quark-antiquark pair being produced, then a particular charm quark and an anti-charm quark, and then it pulled out a pair of down and anti-down from the vacuum, and then these guys could then possibly bind up into so-called D-mesons, which are a particular type of hadron that's made up of a charm and a down quark in this particular example. So roughly speaking, when you produce quarks at colliders, you end up, instead of seeing just a single object, you see a spray of hadronic particles, and we call these things jets. So the event that I showed you earlier was an example of a jet event, and I'll show you another one here. So as you can see, this is a lot messier than an electron or a muon. And so there's this sort of spray of particles, but kind of all roughly bunching up and going in a particular direction. So this is a decent example of a two-jet event at LEP. So you've got back-to-back production of two, most likely quarks, that have then turned into this shower of hadrons. And then each of these hadrons produces a signal in the hadronic calorimeter. So they get stopped by the hadronic calorimeter, and those which are charged will also produce a signal in the electromagnetic calorimeter. So in order to identify a hadron, it's something that has a track and then makes it all the way out through into a hadronic calorimeter. So in order to identify a jet, you're looking for multiple tracks heading in a similar direction and lots of hits in both the electromagnetic and hadronic calorimeters, so the first two layers of the detector. So we've talked about electrons, we've talked about muons, and we've talked about jets. So hopefully we'll be able to identify those three with a reasonable accuracy. There's a fourth object which we need to identify as well, and we'll use those four then to go on and do some actual event analysis. So this fourth object is the tau lepton, or the tauon. So Nick also mentioned this particle as the heaviest partner of the electron. In fact, it's 3,500 times heavier this time. And the difference between the tau and the muon, which is the heavy partner, the other heavy partner of the electron, is that the tau actually decays in flight. It decays before it has the chance to get to the outside of the detector. Typically, it decays actually quite close to the interaction point. So that means that rather than actually looking for taus itself, we actually end up having to look for the decay products of the taus and actually infer that these decay products look like something that could come from a tau. Now, the problem with a tau is that it can decay in many different ways. So Nick mentioned that it can decay, for example, into a tau neutrino and an electron neutrino pair, or a muon neutrino pair. That's a rather clean signature for a tau, but actually they can also decay, and like to quite often decay, into hadrons as well. So a tau neutrino and one or three hadrons. And so it can be quite messy, and indeed it can be quite difficult to distinguish hadronic tau events from just quark events in general, because as you can see in the bottom here, this could well be an event with lots of jets, but it turns out to be an event with a pair of hadronic taus. Okay, so what you're looking for are the two possibilities. If the tau decays into an electron or a muon, then we should just see an electron or a muon. And that's going to be okay for our exercise, because in the end, we're just trying to identify whether the final state involved a lepton or a quark. So we'll get it right if it decays in this particular way. But if the tau decays hadronically and we see something that looks like one or three tracks, so one or three hadrons, basically, tracks with hits in the electromagnetic and the hadronic calorimeter, then we might struggle to distinguish that from a regular quark. But in some cases, are indications that something looks a bit more like a tau than a jet. For example, if you had one distinct hadron coming out of it, for example, in the case of this upper diagram here, where you have a clear charged track and then hits in both calorimeters. Or if you had exactly three tracks as well, that's another way to think that might be a tau. But don't worry about getting it right every time. In fact, even particle physicists do things on an average basis, and there's no guarantee that we're going to be able to correctly identify any given event. Okay, so that's enough for the, oh no, I need to say one more thing. So that's enough for identifying particles. Now, what are we actually looking for in our events? So Nick already mentioned the weak nuclear force. And so we have these weak decays, for example, that are mediated by this force, for example, the decay of a neutron into a proton, and that's mediated by the W boson in particular. So it's a particle that mediates this weak force. And you can see the types of interactions that it has. So it interacts both with quarks and with, say, for example, electrons or muons or taus, which we collectively call leptons. So the weak nuclear decay, Nick described it as a process involving a neutron converting into a proton. What we now know is that something is happening at an even more microscopic level, that the down quark inside the neutron is actually converting into an up-type quark. And this is done by the mediation or the emission of a W boson, which then decays into an electron antineutrino pair, for example. It turns out that the likelihood that such a W decays into any particular final state with which it interacts, so i.e. a pair of quarks or a pair of leptons, is the same. And so if we actually produce lots of Ws at, for example, this LEP experiment, and then count the different ways in which we observe them to decay, and therefore infer the relative probabilities of each of the outcomes, we can actually count how many different types of quarks there are. So that's basically the core of the exercise. I haven't mentioned neutrinos so far, and the reason I rarely mention neutrinos and they're rarely discussed in terms of particle detectors is because they interact so weakly that we just never see them. So they just pass straight through the detector, leave no trace. And it's quite hard to infer that they were there in the first place. So we have to live with that possibility as well. Okay, so we talked about producing a bunch of W bosons at LEP. So in particular, the way in which that happens diagrammatically is the following. So the W bosons have electric charge. And so this is pretty similar to the diagram that Nick showed earlier, where you're colliding an electron and a positron together. They produce some intermediate particle, could be the photon, could also be another neutral boson called the Z boson. And these interact with W bosons such that if you have enough energy, which is greater than twice the mass of the W boson, then you can produce a pair of these guys and then observe the decay quarks at LEP. So these are the types of events that we're going to be looking at. Now, as I mentioned, each W boson can then decay either into an electron, a muon, or a tau, plus its partner neutrino. So that would be so-called leptonic decay. Or it can decay into a pair of quarks. And those would produce, of course, the jets that we mentioned, so those sprays of hadronic particles in the detector. And our task is going to be to identify the different types of events that can come from the production of a pair of W particles at the LEP collider. So roughly speaking, you can imagine the different types of signatures that could happen. So you have one W plus and another W minus get produced, and then each of them can decay either hadronically or leptonically. So we have these two possibilities here, and then that turns into this grid here. So if both of them decay hadronically, then we'll have an event with 4 jets. That's called a double hadronic decay. If both of them decay leptonically, then that's going to be this little segment over here, and that's called a double leptonic decay. Or you could have that one decays hadronically and the other decays leptonically. So that's these two off-diagonal entries here, where you would see something that looks like 2 jets and then an electron, a muon, or a tau. And that was what we call a semi-leptonic or mixed decay. So our task is going to be to identify each of these events and tag them as either one of these 3 possibilities. So a hadronic one, a double hadronic one, a double leptonic one, or a mixed one. Okay. So now it's time for us to actually become a particle physicist and see if we can correctly identify these different WW decay events. So we're going to use some actual events from the LEP detector and try and count the number of types of decays. And so, of course, there's a fair amount of information to take on there. So what we have done is produced somewhat of a summary / cheat sheet that you can maybe refer to while you actually go through the exercise. So hopefully, using this link, you can access a folder which contains the worksheet / cheat sheet PDF file in your on your computer, perhaps while you answer the questions using your phone. That's one option, or you can maybe have 2 windows next to each other to just remind yourself what we're looking for. Okay, and so we'll start by looking at a couple of events together, and then we can perhaps then open the floor to the public and see what you guys can do. All right. So if there are any questions at this point, maybe I can just pause for a sec. And you can go and ask in the chat, and maybe somebody can read the question to me if they see it in the chat. Otherwise, let's move on to the first event. Okay, so hopefully on your Vivox app, you can now see a visualization of one of these LEP events. I've also zoomed into it here, so you can look at it. And let me just take you through my thought process here, uh, and um, and then sort of tell you what I think the answer is, and then we can go through maybe three events, and then we can open it then to the public. So what I see here are two clean tracks, which is quite nice. Um, but I also see deposits both in the electromagnetic and the hadronic calorimeters. Okay, so if this was an electron, then most likely it would have deposited all of its energy in the hadronic calorimeter. And in particular, what I find strange is that the track doesn't point to the actual main energy deposit here, which is this white block here. So to me, this looks like a sign of a tau, okay, because a tau which is decayed hadronically. And I see something kind of similar on the other side, although perhaps this could even actually be a lepton. Or an electron, sorry, because this track is actually pointing towards the main energy deposit, and although there is a little bit of deposits in the hadronic calorimeter, it's very small, as you can see by the yellow color. So what this is telling me is that this is an event which involves a tau, most probably, and an electron, most probably, and that means that it's a double leptonic event. So each decay, each W decayed leptonically, and I can see that everybody's on board with that. Even before I was talking, you guys had already started to put double leptonic. So just to let you know, I'm keeping a tally, and then we can total everything up later. Okay, very good. So let's move on to the next one. We've identified a double leptonic decay involving a tau, which is a good challenge. Okay, so this event, nice and clean. It might even be one of the events that I showed you as an example earlier. So what I can see here again is the presence of two tracks, and those tracks are completely stopped by the first layer, i.e. the electromagnetic magnetic calorimeter. So this is a surefire 100% evidence of an electron, close to 100% anyway. And that's happening on both sides. So we clearly have a double leptonic decay here because of the fact that an electron is a lepton. So remember that lepton means electron, muon, or tau, and hadron means quark, which I think we'll see an example of very shortly. So we've started off with two double leptonic events. Now we move on again. This one looks a lot messier, doesn't it? And so this is a clear example of some jets that I mentioned. So these sprays of hadronic particles. And I can almost identify kind of four kind of axes that the energy is being showered at. So I've got one up here, one in this direction, and then roughly speaking, two in these two directions here. So to me, this is very much likely to be a double hadronic decay, as most of you have said. Now, it's true that it could be a mixed decay in that one of these could be a tau, but I think this looks more like the presence of four individual quarks being produced and showering into these hadronic jets. So mixed wouldn't be definitely wrong, but I think it's more likely to be a double hadronic decay. Okay, so now we've gone through three events together. Now I'm going to show you the next event and not say too much about it and let you guys decide. And then I might perhaps comment on the answer, depending on what we get. And I'll leave you sort of maybe 10, 20 seconds to have a think about it. I'll also zoom in, just in case you can't see it well on your device. All right, so let's see what everybody has said. Oh, you guys are on the ball. So this is definitely, I would 100% agree with you that it's a mixed decay. And the reason being that we have a clear electron here, as you've all identified, by this guy, this little white dude, being stopped entirely by the electromagnetic calorimeter. And then the rest of the event looks pretty jetty to me, so it's probably a pair of quarks that have been roughly produced in these two directions here. So great job on that one. Let's move on to the next. ideally, we want to get through as many as we can so that we have enough statistics to say something interesting about the number of quarks. So I'll probably decrease the amount of time that we have between each one as we go forward. And we probably have something like 10, maybe 15 minutes of looking at events before we have to summarize. So what have we all got from this? Yep, definite double hadronic decay. Excellent. So most of you have responded, so I'll move on. Next one. Pretty messy event overall. Yeah, this one is a bit less clear whether it's mixed or double hadronic. I'll agree with you there. But yeah, I think it's still clearly showing 4 jet-like structures. So I would lean towards a double hadronic for this one, which is confirmed by the majority. So don't worry about changing your answer if you think you got it wrong. It doesn't really matter. I'm just going to go with the majority answer anyway. All right, next one. This one looks perhaps a bit more atypical. Yep, I think I agree with you there. Double leptonic, single tracks, pretty much entirely stopped by the calorimeter here. Although it's a bit strange to see these crosses here, which are supposed to be muon hits. So it could even be a muon actually. It could even be a pair of muons, but they certainly look more leptonic than anything else. So I'll agree with you there on the double leptonic. What about this one? Yeah, pretty unanimous on the mixed here. Once again, some events are much more obvious than others. Here we have a clear electron and a pair of jets, right? So that's an electron and a quark going in these 2 different directions, producing these sprays of hadrons. So that's definitely a mixed decay. On to the next. By the way, Pearl or Nick, if you can let me know when I have about 10 minutes left, that would be good, so that we can move on to the analysis.
Will do.
Thanks. Ooh, this one is a bit harder to decide. It's a pretty messy event. So you guys are undecided between double hadronic and mixed. You've gone for mixed. Let's go with that. On to the next. Okay, looks like pretty clear majority for double hadronic there. Oops. So No, oh yeah, okay. This one's a little trickier, perhaps. Again, one of those ones where you might not be sure whether it's a tau or a jet, and therefore whether it's a double hadronic or a mixed. This is probably one that even I'm not too sure, to be honest. So let's go with the majority on that one. Mixed decay. Next one. Yeah, another one where it's not too easy to tell between double hadronic and mixed. Remember that a hadronic event leads to two quarks, which leads to two jets, whereas a leptonic event that involves a tau will lead to kind of one object that looks like a tau, either a something like a single hadron or three hadrons, kind of all pointing in one direction. So if you have a double hadronic event, then there should more or less look like four objects going in different directions, although sometimes it's hard to because they overlap with each other. Whereas in the case of a mixed one involving a tau, there would probably be more like three prongs to the event rather than four. All right, so we've gone with mixed for that one. This is a funny one. Yeah, so pretty clear evidence of muons here, as you've all correctly identified. Although strangely enough, it hasn't left a visible track, which is a bit strange. Maybe the tracker was not quite functioning correctly in this event, in this particular recording of this event. But I agree with you that it's a double electronic event. Yeah, this one's definitely looks like a double hadronic to me. All right, I'm going to try and pick up the pace a little bit now so that we get through a decent number of events. So once most of you hopefully have responded, we can move on to the next one, once it looks like there's a clear majority in any case.
So Ken, you've got about 10 minutes at this point.
Okay, maybe we'll do another 5 or so, and then we'll move on. Quick 5. So agreed with you, that's a double hadronic. All right. Next one. I'm going to try and do about 10-15 seconds between these events, just so we don't run out of time at the end. Excellent. Mixed decay. Fully agree. Oh, it's tight between double hadronic and mixed, but I'm actually going to agree with the mixed crowd. I think it's the mixed event as well, because this thing has 3 tracks. So it looks like 3 hadrons. So it could well have come from a single tau, and generally the event is more 3-pronged than 4-pronged. Right, 3 more. This is looking pretty unanimous on the double hadronic front. So I'm going to agree with you there. Next one. Bit of a mess, this one. couple that don't knows. I'm not surprised. It's a bit tricky, but it looks like double hadronic is winning out. You'll probably agree with that. All right, second last one. Right, so I see a clear preference here for a mixed decay, which I'll agree with. This looks like an electron, and these look like a pair of quarks, which have turned into jets. So mixed. And final event, before we move on to the analysis. Nice messy one to finish with. Looks like you've mostly gone for double hadronic. Tempted to agree there, although it maybe could be a mixed as well. Nothing is certain in science, as we know. Okie doke, so of course we could keep going if we had more time. There's about 100 events to look through. So it's a shame that we have to stop, but of course it's good to do a bit of analysis at the end before we wrap up. So hopefully that was kind of fun, and we can now take a look at what kind of results we got and what kind of results we expect. So let's think about the predictions. So what could we possibly expect? So we are trying to count the number of types of ways in which the W can decay into quarks. So the number of quarks, basically. So this is a similar version of the table that I showed you earlier, except now we're counting possibilities. Okay, so as we said, each W can decay either hadronically or leptonically. Now we know that there are 3 types of leptons: electron, muon, and tau, and we're postulating that there are n types of quarks, and that's the quantity that we're trying to infer from the data. So that means that looking at the relative probability of all of them, we can see how many ways are there in which each type of decay can happen. So when we think about the fully hadronic case, well, there are n possibilities for one and n possibilities for the other. So there are n squared possibilities for this type of decay. And conversely, for the fully leptonic case, there are 3 times 3 possibilities. So that's 9. Now for the mixed one, we have that the first guy can decay leptonically, that's 3, and then the other guy decays hadronically, that's n. So that's 3n possibilities, but of course it could have happened the other way around, right? So there are 2 times 3n possibilities. And so when you think about the probability of a certain decay type, then that's basically can be measured as the number of ways that it can happen if they're all equally likely, which I've told you they are. The number of ways in which it can happen divided by the total number of all possible types. Okay, so this total would be the sum of these 4 values here. And so the probability of a double hadronic decay is therefore proportional to n squared, and it's equal to n squared divided by the total number, which we don't have to write out because it doesn't matter in the end for the calculation. Same goes for the double leptonic, 9 divided by the total number, and then same goes for the mixed, 2 times 3n, so 6n times divided by the total. Okay, so these are our predictions. And so this is the summary again. So we know there are 3 sorts of leptons. There are 9 ways. What did we see? I can tell you that we saw 4 double leptonic decays. Okay. If there are n quarks, we expect n squared of those. And I can tell you that we saw 9 of those. And then for the mixed, we saw 8. Okay. And now the reason why we don't care about this total is that, as we said, each decay type should be observed according to its relative probability. So the number of events of each type that we observe should be proportional to the probability that we expect to observe it. And so if we divide the numbers of events that we observe or do some algebra between these different probabilities, then we can, for example, solve for this number of quarks n as being 6 times the number of double hadronic events that we observed divided by the number of mixed events we observed, for example. So you can get that just by solving equations, by taking ratios of these probabilities. You see that the total drops out, and then you end up with a nice equation in terms of the number of each event that we observe, each type that we observed, as a function of n, which you can then solve for n, right? And there are actually 3 different ways we can do that, right? Because we observe 3 different types of events, and so we can take 3 pairings of the different types of events that we observe to solve for n. And so we can actually have 3 different measurements of n. So let's quickly do that on my phone calculator if I can. So for example, 6 times the number of double hadronic events, 6 times 9, divided by the number of mixed events, 8. And so we get an n of 6.75. Okay, so let's note that down, 6.75. We can do the same thing with the second equation. So now that is instead the square root of the number of double hadronic divided by the number of double leptonic, which is 4. So 9 divided by 4. Okay, and then multiply that by 3, and we get 4.5. And then lastly, we can do 3/2 times the number of mixed events divided by the number of double leptonic events, which is 4. And apparently we get 3. Did I do that right? Mixed is 8. I think I did. Oh yeah, that's right. We get 3. Okay, so a little bit of a spread of numbers. So we got 3 different predictions for n. There was a bit of a spread of them. And we see that it's either 6.75, 5, or 3. And so maybe the average of those would be something like 5 point something, I would say. Okay, so in the end, using our data, using real events from LEP, looking at decays of W bosons, we've inferred some number, which should be the number of types of quark decays that a W boson can have. And that number we found to be on the order of 5 point something. So that's, using real data, we've actually found something about nature. And so how does that correspond to what we should have got? All right. So what we know based on essentially the mass of the W boson and the different types of quarks that we have, it turns out that the W boson can decay either into a pair of up and down quark pair. So these guys are partners as far as the weak interaction goes, or it can decay into a charm and strange quark pair. So the charm is the heavier copy of the up, the strange is the heavier copy of the down. As for the 3rd generation, there's also the top and the bottom quark, but the problem is, as Nick mentioned, the top is the heaviest particle known to us, the heaviest fundamental particle in the so-called standard model, and it turns out that it's heavier than W boson, which means that the W boson at rest doesn't have enough energy to decay into a top-bottom pair. Even though it does interact with them, it can't decay into them when you produce it at the collider. So it looks like there are 2 different ways in which the W is decayed. However, the number that we've got is actually a lot closer to 6 than it is to 2, right? 5 point something. And the reason is that there is actually an additional factor of 3 that exists. And so the correct number of ways in which the W can decay into quarks is actually 6. And the reason is that these quarks are particles which interact with this strong force, the strong nuclear force that Nick mentioned. And this strong force is analogous to the electromagnetic force in that anything that interacts under that force has a certain strong charge, which is the analog of electric charge. However, the main difference between the strong force and, say, the electromagnetic force is that there's 3 different types of charges under the strong force, which we very creatively label as red, green, and blue. And so each quark actually has secretly 3 different copies of itself, which have different strong charges. And so you might think that there's actually 1 up quark, but actually there's 3 types of up quarks. And so for each quark decay, although for each of these different types of quark decay, so the up and down one or the charm and strange one, there are actually 3 possibilities. So that depending on the charge, the color charge, so-called color charge of these final states. And so rather than having 2 possibilities, we actually have 2 times 3 possibilities, which is 6. And so based on our analysis, it actually looks like we got pretty close to the number 6, which I'm quite pleased with because we didn't obviously get through that many events. And so I think we got quite lucky there and did quite well. Good. So hopefully that's sort of giving you a flavor of the kind of things that we can do. It's obviously a very simplified exercise. I just wanted to flash you to finish what's going on in terms of the state of the art. So, Nick already mentioned that LEPS doesn't exist anymore. It's actually the LHC, which has replaced the LEP collider and which collides protons. These again are visualizations of the detectors at the collider. You can see that they have a pretty much similar layered structure. And so the principles are basically the same. We're just dealing with a much higher energy and a different initial state, which leads to different possibilities in terms of the kinds of particles that we can observe. And so here's an example of an event display of the LHC. So of course our graphical capabilities have also gotten a bit fancier. And so you can see that it looks nicer for starters, but also that these proton-proton collisions are actually much messier. So you can see that there's really a real mess of spray of different hadronic particles happening. And this is related also to something that Nick mentioned, which is the fact that there are actually multiple interactions, proton-proton interactions happening per bunch crossing. So if you look at it in the horizontal direction, you can see how many different potentially interesting interactions are happening at any given time that we take a picture of the detector, but only one of these is actually interesting. Okay? So this is actually an example of a Higgs boson candidate event decaying into a pair of electrons, which you can see with the green lines, and then the 2 muons that you can see as the red lines passing all the way through the detector. And of course, modern analyses are much more complicated than just looking at them by eye. They use complex algorithms and AI to actually get interesting physics out of it. And so you can use these links here to have a look at some other event displays as well. And I just added this slide whilst Nick was talking because he asked one of the questions about how does the Higgs boson couple, and so what do we know so far? And this is a very nice summary plot about what we know about the Higgs so far. And so this is a plot that compares the mass of a particular particle that's in the standard model. So you can see, for example, the different muon, the tau, the W boson that I mentioned earlier, and how strongly we've observed it to couple to the Higgs boson. And so because the Higgs boson, as Nick mentioned, is responsible for giving mass to these fundamental particles, we expect their interaction to be proportional to the mass of the particle. And so we can draw this beautiful straight line through the data that we've got so far, and so far confirming indeed that the Higgs boson couples in the way that we expect. So I think this is a really nice summary plot from the LHC experiment. And with that, I just thank you for your time. I hope you enjoyed it, and leave you with a picture of myself visiting the Atlas detector cavern when the beams were still switched off last November, as you kind of get an idea of how big these things are. And maybe one day that'll be you as well. So thanks for your time.